Okay. So just gonna take questions from the practice test 1 and 2. Okay. So if you guys have any questions from either one of those two, just raise your hand, point it out to me, and then I can solve it up for you. Um, if you guys don't have any questions and have like some topics you want to discuss, like box plots or like any topics you are confused in, just tell me, and then we'll go over that as well. So, any questions from the practice test, or do you? Yes. Like if we're going to need a plot where histogram was is asking because for one of the questions it asks what touch diagram that's okay. What question is that? Um, 13. Yeah. So, I mean, just look at this question, right? So what is the nature of data that you're collecting? Is so you have households and you have like 100 of these households, and for each household, what you're doing is um, the utility bills for each household, right? And we have 100 households. So this is the nature of data that is being collected. For each of the household, Sam is asking, what is the utility bill? So the question is, what is the best way to represent this data set? Um, and I mean, the answer is a time series plot, okay? Um, and it's not only utility bills, but it's utility bills over past 12 months. So the data is more like this. Sorry. Um, let me write here. So this is what he's collecting, right? For the 100 households, he's asking what is the utility bill for the entire 12-month range. So the best way to represent this is in a time series format because we are collecting over time. We're collecting over 12 months. So time series makes the best sense. It'll be something like this. You have time on the x-axis, so you have all the 12 months here, 4 up to 12. And for each for let's say household 1, right? Household 1, you see how this is changing. It's for household 2, you see how the utility bill is changing, and you do it for all of the households, right? So this is the best way, given this nature of the data set, you're collecting. This time series format is the best way to visualize the data set. Okay, that makes sense. And time series are usually useful when you have data that changes with time. You have the same variable. The variable is the utility bill, but we are collecting over different time periods, right? So this will make the most sense while visualizing the data set. Out of all of the other options, pie chart, bar plot, they are all a good thing to visualize, but since we have time, we need a time series plot. Okay, this makes sense. Any follow-up questions on this? No. Any other question from the test? Yes.
20, question 26, 29. Looking kind of at, I guess, the probability.
Okay. On the version. Okay, sure. 20. What did you say?
26, 29.
26 to 29. Okay, sure. Sure. So I don't know if I can copy this over there, but
Okay.
this question, right? So what is this question giving you? So I want everybody to read it so we can go over it. So it's a CNN exit poll on the 2020 Democratic election in New Hampshire. And S, so you have two events here. S is the event of supporting Sanders, and Y is the event of being from in the age range of 18 to 29. So you have this table, and each entry of the table gives you different people who support different people, right? So 183 people who are age 18 to 29 support Sanders, 78 support Buttigieg, and 129 support other, and so on. So this gives you the count of people that support different people and also the different age group they belong to, right? So this data set is clear, right? What's happening? Um, so what is the first question? What is the probability of S and Y? So let me write this. So S is the event of supporting Sanders, and Y is the event of what? Being 18 to 29, right? So the question is, what is the probability of S and Y? The first question is probability of S and Y. How do you do this? So what does S and Y mean? How do I write this in terms of events operations? And means what? Intersection, right? Um, and what is the formula for intersection? This? And when is this true? Are you sure this is the formula?
Well, minus.
Yeah, I don't think this is the right formula. Okay, so P of, give me a second here. I mean, yeah, you can do it multiple ways. Okay, so what is the general formula of probability of an event? How do you find the probability of any event? The most general formula to find the probability of any event is what? How do you find it?
Number total. I mean, the number of event over the total.
It's the number of times the event occurs divided by the total number of possible events. So you can use this same logic here. So it's asking what is the probability that somebody is between age 18 and 29 and they also support standards, right? So that's what this is asking. So the number of people who support Sanders and are 18 to 29 divided by the total number of people. Right? The probability of any event is the number of times that event occurs divided by the total possible events. And we are using that same general formula here. So what is the numerator here? How many people support Sanders and they are 18 to 29 based on this table? 183, right? So, and what is the total number of people that are, what is the total number of possible events? 3,000, right? So it's 183 over 3,000. You can just do this. Yeah. This makes sense? I'm just using the most basic formula. I mean, you can do a bunch of other things too. Like you can, write this as S given Y, probability of Y, and try to solve using this method as well. But this one is the most simple one. Okay.
Does it matter depending on whether the events are in
Yeah, it does matter. Yeah, because things changes when um, they're independent, and when they're mutually exclusive, right? The equation changes.
so like for this, like probability test of why will first have to determine whether they're independent or not?
Yeah. Yeah. Um, and they are independent sort of events, right? I mean, somebody being in the age of 18 to 29 does not have anything to do with whether they support Sanders or not. Um, so this is how you do the first one. So let me go to the second one. What is probability of S given Y? Now, what is the formula for this? Yeah, probability of S and Y happening together divided by the probability of Y, right? So we already found this here, right? Probability of S and Y is 183 over 3,000. So this is 1 over 3,000. What is the probability of somebody voting for somebody being in the age of 18 to 29? What is the probability of Y? The probability of Y is, again, how many times Y occurs divided by the total number of events, right? So just using the basic formula. So how many 18 to 29 are there in this data set? 390, right? And then divided by how much? 3,000. Okay, so 390. Um, whatever this answer is, it's 0.469. Okay. This is clear, right? Let me go to the next question. Is how do you do this? Based on the information in the table, is being 18 to 29 independent of supporting Sanders? So what is this? This is actually asking is are Y and S independent events, right? Because this event 18 to 29 is your Y, and supporting Sanders is your S, right? So saying, are these two events independent or not? So how do you check for independence? How do you check if two things are independent or not? Anybody? Uh, that's mutually exclusive. So yeah, let me write that down too. So mutually exclusive and independent events are two different things. Okay, so mutually exclusive means they cannot, the two events cannot happen at the same time, right? One example will be, when you like pick a card out of a deck of card, you cannot choose a heart and a spade at the same time, right? So those two events are mutually exclusive events. So what happens when things are mutually exclusive? So let me just go down this chain of thought. So so let's say event A is, there's an event, B is another event. Okay. First event, any event. If I say A and B are mutually exclusive, then what is this?
What is this?
If A and B cannot happen at the same time, what is the probability of A intersection B? Zero, right? So, okay. And A union B is just P of A plus P of B, right? Usually it's minus P A intersection B, but this thing goes to zero. The A intersection B goes to zero. So you have to be careful when, if things are mutually exclusive, you have to check if this is true or not. And in this formula, if you're asked what is the union, what is the probability of the union of two events, then you have this goes to zero. So it's just probability of A plus probability of B. Okay, does that make sense? Yeah. And this being zero is very intuitive, right? A and B, if they cannot happen together, then their probability is zero, and it's as simple as that. Um, so this is when things are mutually exclusive. Now, independent means the probability of one outcome is not affected by the other outcome. Okay, one event, probability of one event is not affected by the other event. One example of independence will be, if you if you toss a coin two times, the probability of getting heads in the first toss and the probability of getting heads in the second toss, uh, it's the same, right? They're independent events. It's not one event is not getting affected by another event. It does not have anything to do with it. So if when mutually exclusive, this equation holds, what about when they're independent? What is this? Equal to when is probability of A, and probability of B given A is just probability of B, right? Uh, Slideshow cards. Okay. So what is the intuition behind this being true is, A given B is still A. Given B, A has not changed, or the outcome of A is not affected when things are independent. Okay, like probability of getting heads, given A&M wins SEC, right? What is this? What are these two events? Independent, right? And what is, so based on this general formula, what is the probability? What does this comes down to? Probability of getting heads, and that is just 1/2, right? So when you condition on an event that is independent of the other event, the probability is still getting heads, okay? A&M winning SEC, uh, a thunderstorm on a Monday, things like that does not affect this event. So all of those events are independent. So that's sort of the intuitive way to like think about it. Given B, the probability of A is not affected. Given A, the probability of B is not affected. Still the same. Make sense? Um, so how would you check for this? Are Y and S independent? If Y and S are independent, what happens? Then probability of S given Y is just the probability of Y. Probability of S. You guys can see this, right? Or do I need to write bigger, like a little bit bigger? Yeah, it's okay. Probability of S and probability of Y given S is the probability of Y. These two things hold. If Y and S are independent, then when you check, if you can check if this is true or not. If this is true, then Y and S are independent, right? So we already, let's work with equation 1. Okay, so we already know this. We already calculated this in part 2, okay? And this S given Y is 0.469. So this is 0.469. What is the probability of S? Did you already find that? So you have to, I think, go back to the table. What is the probability of somebody supporting Sanders? So what is the probability of somebody supporting Sanders based on this table? 792 out of 3,000, right? You just see how many people support Sanders out of the total number of people, and 792 people support Sanders. Again, probability of any event is the number of time that event occurs divided by the total number of events. So 792. So can somebody tell me what this is? 4. So are they independent or not independent? They're not independent, right? Probability of S given Y is not equal to probability of S. And you don't have to check for both. You can just check for one. Since we already calculated this, I chose to go the first route, but you can also go the second route. Depends on what you have already calculated or what is already given to you in the question. So S and Y are not independent. Okay. And I think that's what, yeah. So you just check this and they are not independent. Okay. Any question on this? What is P of Y or S? What does or mean? What do I replace this with here? Union, right? And now what is the formula for this is P of y plus P of s minus P of y intersection s. Um, what is the probability of y? Probability of y is 390 over 3000, right? 390 over plus the probability of somebody supporting Sanders. We just did that, 0.264, right? Let me write it in terms of 792 over 3000. And what is the probability of y intersection s? I think we already did that too. No? In the first part, in the first question, we already found p of s and y. So it's 183 out of 3000, right? So it's whatever this number is. Sorry? Let me check with the actual thing. Yeah, 0.33. Okay. So this one is simple. Just use the basic union formula. Probability of y, probability s, probability of y intersection s. Again, if so these they are not mutually exclusive events. Okay, that's why this is not zero. If things were mutually exclusive, this will have been zero, and then you just need to use this. Any questions? No? So so this is another question. So no question on this Bernie Sanders and or this election data set. No, right? Okay. So let's move on to the um, let's move on to this question. So let me just copy paste the question. Okay. So you have to check for two things. Okay, given this question, you have to check for two things. Are event A and B mutually exclusive? Are they independent? So what is given to you? Probability of A. So we don't know what A and B are, okay? We just two random events with their probabilities given. So probability of A is probability of A given B is 0.5. So what does this immediately tell you? They are independent, right? Probability of A given B is just the probability of A. So it's independent. What about mutually exclusive? How do you check for if things are mutually exclusive or not? How do you check? I just mentioned, so you have to check for this, right? Probability of A intersection B. If things are mutually exclusive means they cannot happen at the same time. So the probability of two events intersecting is 0. So that's what I check for. Um, You guys know this formula, right? Probability of A given B is probability of A intersection B divided by probability of B. Probability of A given B is 0.5 from the top, and probability of this is probability of B. We don't know. Are you guys following what I'm doing? So I'm checking if this is 0 or not. I use this general conditional formula. Probability of A given B is A intersection B divided by probability of B. I moved A intersection B to this side. So the formula changes to this. Now, when is this 0? When is this thing 0? When the probability of P is 0, right? Then only and only then. So let me write it again. Probability of A intersection B is probability of A given B times the probability of P. So we want this to be 0, right? But this is not 0. This is 0.5. It's already given in the question. It's 0.5. And this is not given. So for this thing to be 0, probability of B must be 0. And only then this thing will be 0. Probability of A intersection. Does that make sense? So for A and B to be mutually exclusive, probability of B must be 0. Only when this is true, then A and B are mutually exclusive. But probability of any event being 0 means what? That means that that event does not occur at all, right? So this cannot be true. Um, so this is my reasoning for claiming that A and B are not mutually exclusive. For A and B to be mutually exclusive, the probability of some event has to be 0, and this is theoretically possible, but not practically possible. Okay, because everything has some probability. It might not happen. Uh, it might not, snow right now. Okay, right at this moment, it might not snow in College Station, but it has some probability, 0.0001. So stating that probability of something is exactly 0 is not reasonable. Okay, so that's why we can conclude that A and B are not mutually exclusive, because the probability of any event will not be 0, even if it's very less likely to happen. Okay, does this make sense? Any follow-up questions on this? This is the question. Okay. Like both independent and mutually exclusive. Yeah, I think so. Like if you roll two different dice. So let me write down. Okay. So this is your first die, and then your event, let me call it A, is rolling 1 out of 6, 1, 3, 4, 5, 6, and this is Event B, this is die 1, this is the dice 2, so rolling 1 again. So what about these two events? What about their independence and mutually exclusive? Are they independent? They are independent, right? Getting your probability of getting 1 in the first die does not affect the probability of getting 1 on the second die. So A and B are independent, and you don't even need to check, you don't need this right now because we're not doing mathematical things here. So A and B are independent. What about mutually exclusive? Can these two events happen at the same time? Can they? They can, right? So they are not mutually exclusive. So A and B are not mutually exclusive. Meaning they can happen at the same time. This is an example you wanted, right? Both. Okay. Okay. So yeah. So when you have two events, check if they are independent or not, if they are mutually exclusive or not. There are different ways to do it. If you know what the event is, then you can sort of do it intuitively. But if you're not, if you don't know the event, but instead are given, instead are given the probabilities for them. So in this case, you don't know what A and B are exactly, right? But you know the probabilities for them. But still here, you can still check for independence and mutual exclusiveness by using the mathematical definition. So you can work intuitively, or you can more. The best way to do is to check for these formulas if they hold or not, right? So if they is to check if these things hold or not. Um, okay, so let me do another one. Let's do this one. So insert blank. Question 3. So okay, so let me do this one. So what are the given? So what are the given things here? So what is? So let me. So Jim tosses a fair coin to decide whether his next vacation will be in Hawaii or Alaska, right? So let's deal with this first line here. So what is the probability of him going to Hawaii? 50%, right? He's tossing a fair coin. So he can either go to Hawaii or Alaska with 50-50 probability. So probability of H is, let's say H means Hawaii is 0.50, and probability of Alaska is also 0.50. What about this part? If in Hawaii, Jim is surfing during the vacation with a probability of 0.9, if he goes to Hawaii, the probability that he'll be surfing is 90%. If he goes to Alaska, the probability that he's surfing is 10%. Okay, so how do you write it down? Sorry, you add them. Use a tree diagram. Okay, but like, how will you write this probability? Yeah, right. So probability that he surfs given that he is in Alaska, and probably that surfs given that he's in Hawaii. So this is 0.1. This is 0.9, right? So this is a conditional probability statement that is given in the question. Given that he goes to either of the two places, the probability of him surfing is the following. And it also makes sense, right? If he goes to Hawaii, it's more likely he surfs than he goes to Alaska. Um, I don't know if you can surf in Alaska. So so these are all the things that are given to you. Okay, so these are given in the question. Um, what is the question now? Given that we know that Jim went to surfing during the vacation, what is the conditional probability that his vacation was in Alaska? So how do you write this question in terms of probability? Probability of something we have to find. What is that What is that event? What is the event that is being asked in this question? Yeah, right. Probably. What is the probability that? Okay, thank God. So probably that he was in Alaska, given that he went surfing. Is what? So this is the probability question, and all of these things are given to you, and you have to find this. Okay. It's this. This is like me telling you that I don't know where Jim went, but he definitely surfed. What would be the chance he went to Alaska, right? So this is me saying that to you. Given that he surfed, given that we know the only information we know is that he surfed, we have to find out what is the probability of him going to Alaska and what is the probability of him going to Hawaii. So how do you solve for this? P of A given S.
And that over um,
Yeah. So what is the probability of A and S? How do you find that? So let me just write equation 1, okay? So what is the probability of A and S? Let's say numerator. How do you find this? Sorry. Okay. So how do you find this? 0.5 times 0.1. So what formula are you using? Just tell me that. But this is true only when A and S are independent. But A and S are dependent events, right? Him surfing is dependent on which city he goes, and which city he goes is dependent on whether he surfs or not. So they are independent events. So this is not true, or you cannot use this for this case. Okay. Um, what about this? What probability of S given A is probability of A? Sorry, let me write it right down. So what we have to use, let me get to the this is probability of A. Okay, so probability of A. I want to use this formula. So what is the probability of A intersection S? Probability of S intersection A times probability of A, right? Can I use this? Yes, right? Because S given A is given to me, and probability of A is also given to me. Now you replace this in the equation 1. What do you get? You get probability of S given A times the probability of A divided by probability of S. Okay, and this thing is called the Bayes theorem. I'm sure you guys have read on that. Does it make sense? I know it's complicated, so let me write it again. Okay. Do you guys know Bayes theorem first? It's taught, right? So probability of A given S, if you look at the Bayes theorem, it's basically probability of S given A times probability of A divided by probability of S. This is the Bayes theorem. This is what you have to use here. Okay. Now, instead of writing this directly, I was just showing you how it actually comes to play. You use the general formula. Probability of A given S is the probability of intersection divided by the probability of S. And this numerator becomes this. Okay. And the Bayes formula is here. Okay. So I was just not stating this directly, but showing you how it comes. But this is what you have to use if you are confused on what I did. So what is probability of S given A? 0.1. What is the probability of him going to Alaska? It's 0.5, right? It's tossing a fair coin. And what is the probability of S? Here you have to use law of total probability. So whenever you have a question that involves Bayes theorem, to calculate the denominator, you always have to use the law of total probability. Okay. The law of total probability is the following. Is surfing given Hawaii. This. It's just basically saying how many ways he can surf. This is just this. This is just this. It's saying he can. What is the denominator is saying? What is the probability of surfing? The probability of surfing is the probability of surfing and him being in Hawaii plus the probability of surfing and him being in Alaska. This is called the law of total probability. Okay, it considers all the cases, how the event can happen, and what are all the cases the event can happen? S, right? Either he goes to Hawaii or either he goes to Alaska. So these things are important, okay? So you have to remember the formula, and if you don't want to remember, you can just get to it using what I just did here. Um, and then you have to remember how to get the law of total probability. So what is this? What is the P of S? P of S given H is what? 0.9. 0.9 times P of H is 0.5 plus 0.1 times 0.5, right? So what is this? Can somebody calculate this for me? 0.5. And you just plug this here. It's 0.1 times 0.5 divided by 0.5. So 0.1, right? So let me first check if this is true or not. Okay, 0.1. So this question is interesting, okay, because it makes you test a bunch of things. First, you need to know what is given in the question. Is exactly this is given. You cannot confuse the conditional statements. Okay, given he's in Alaska, the probability of surfing is 0.1, and these things you cannot confuse. And then you have to know what is being asked in the question. Then you have to know the Bayes theorem or the way to get to it and the law of total probability to solve this problem. Okay. Any questions on this? Yes.
Probability of that happening, of course, one. And asking, isn't that sure what was the probability that you'll ask this? Do they not just kind of tell you what the answer is?
I mean, what do you mean? Like, so, I mean, you mean based on this?
Yeah.
I mean, coincidentally, these two things are equal, but they might not be always equal. Yeah, because um, you know, the first one is saying if he goes to Alaska, what is the probability he surfs, right? The second one is saying what is the given that he surfed, what is the probability he's in Alaska? So, I mean, two different things. The events here, because of that, might looks the same. But if you take like another event, like somebody being diagnosed with some disease, and the other event is something, then the two definitions will be completely different. Yeah. Um, and this is what the Bayes theorem is particularly useful when you have information like this, right? S given A is given to you, and you have to find A given S. So whenever you see that sort of thing being asked, might lean towards Bayes theorem. Okay, like this is given to us, and we have to find the opposite thing. Like this is given, and we have to find the opposite thing. The immediate thing that comes to my mind is the Bayes theorem when you see things like this. Um, and you could also do probability of H given S. Okay. So, okay, so that was the probability questions he told me from this slide. Any other questions? You guys have any specific questions? No. What time is it? Oh, okay. Uh, yeah. I mean, if you guys have any questions, feel free to. I'll be here for 8 more minutes. So. Sorry. Yes.
Given that these two events are dependent, right? There's this explanation,
Yeah.
but like it doesn't make sense to me.
Sorry.
Makes sense, but like
5 males to 5 males. Two of the 10 students are chosen at random for a role play. So there are 10 students, 5 are male, 5 are females, 2 are chosen, right? So the first chosen is male, the second chosen is female. The two events are dependent. Um, yes, because when you first choose a male, right, you're randomly picking, right? So let's say you pick a male. In the second, when you go for the second to pick somebody else, then your probability shifts, right? Because the male is less, the probability of being a female is high. Whereas if you had picked a female, then the probability would have changed for both of the two cases. So it depends what you choose the first trial. You can do it mathematically. You can do it mathematically. Don't have a marker with me, but where do I write this? Uh, just check if P of A given B is P of A or not. So, if this is true, then they are independent events. Yeah, and this is, you know, this is this, and you check P of A. Just take these two things are in. You can find the probability of A and B together. Uh, and stuff like that. So I mean, mathematic. You don't have to go mathematical route for this question. It's very yeah, it's very intuitive. Yeah. Yep. See my friends. Yeah, just a sec. Okay, let me see how do I stop recording.